Yeah. Oh, that's all. I mean, better than percentage or better. I just want to give you money. I'm gonna give you money. And where's Mark? You don't have that introvert. I mean, they are down if that's what and put it on. So they operate they yeah, that's it. Yeah. You don't have to say that now. I do. Talking about you work $50. That's like two. Yeah. You don't want to be doing something for an entire year. Is this the truth? About a car. A car you would bring like nothing. Significantly more expensive than $20. Yeah. But I am, you're 18. Yes, you do. I guess I'll try. Okay. Oh, shit. I don't know why you're like. Dude, I'm just like, I got 50 days. It's not $200. I got 15 like second page. So like, I'm working at it. Yeah. And I'll stop on the right. I'm not become a server. Or you just self-employed at. Like, I'm a little bit. Oh, like, I didn't do a rate or something. I thought it was here. I did. I'm not sure, but I very much. I like. That's like I couldn't get it. I was just where someone's gonna. I messed up about power. Well, I didn't mess it up. I opened up. No, I didn't. I messed it up. I literally just took forever to figure out how to do it. They explain what the power. Dude. Well, we used to. Well, we used the hard derivatives from the recovery. I can't even do it. We used the hard. Used the derivative. It's the denominator threw me off. It was a denominator of 100. Yeah, literally. There we go. Yeah. I'll be at the end of the Big back. So good. Out 310. Yeah, I knew that about my so or my mistakes. I only have anyone on. Yeah, not in person. You don't get your first stuff. I will take it up. Well, I mean, it's better than going to class for 3 hours. That's why it's like an egg. Sorry, Wayne. We should. I said stupid, that's why I break that. Ooh, yeah, me. Oh, great.
Okay, so any questions before we get started? So the exam will be next week, right? And what we're going to do today is actually going to finish chapter 15 using one question to tell you what I mean by the small x approximation. And after that, we actually go through the return to review hangout. And there are actually 18 questions on the hangout. I'm not sure how many we can actually go through today, but the target is actually we go through is half of it. Okay, so that's our plan. Okay, you guys ready? Any questions? Okay, so the first thing is actually for the very last part for chapter 15, we want to talk about is the small x approximation. Okay, so this is a typical question you're going to see that. Okay, so let's read this question carefully. It says the KSP of AlOH3 is certain number. What is the solubility of lead insoluble salt in a 0.01 m AlNO33? Okay, so in this chapter, one of the questions you're going to see a lot is that it's asking you about the solubility of the insoluble salt, right? So when you read the question, the first thing is actually to identify what is actually insoluble salt in the questions. Okay, so you have two species inside this question, right? One is AlOH3, the other one is actually AlNO33, right? Which one is actually is your insoluble salt? You have this, you have lead, right? You have two compounds inside this question. Which one is actually your insoluble salt? AlOH3, right? How do you know? Yes, that's the key. And if you see the KSP of certain species, that certain species is an insoluble salt. Let me take the species into to write out the chemical equation. Okay? So then what is actually the other species? The other species will be actually a soluble salt. And it's going to be associated to produce some ions. That is actually the same ions you're going to produce from your insoluble salt. Okay, so let's look at this. Can you guess which ion is actually the ion that your soluble salt is going to contribute to your insoluble salt? Yes, so that is actually why I say the common ion effects. Okay, so this one will actually goes into your chemical equation when you calculate your solubility. All right, so that's a basic fundamental knowledge that you have. If you have that concept, then solving the problem is actually quite straightforward. Okay, so questions. You want you to solve the solubility, right? So I use S to represent the solubility of AlOH3. Okay. Then we look at what kind of data that we have. Since you know AlOH3 is actually insoluble salt, then you should actually write out its chemical equations, right? And then by now you should know that actually to memorize, when you see Al, it has to be 3 plus once it dissociates, right? And then OH always carries -1 charges, but you have 3 of length. Okay, so let's actually how you write out the chemical equation. Okay, and you should also know that the KSP of insoluble salt will only be the product of its ionic species, Al3 plus times your OH minus raised to a third power, right? So let's say actually the things you should actually definitely write out whenever time sees KSP problem. Okay. Then the next thing you should know is actually the solubility you want to write out is this, right? The solubility of your insoluble salt, which means that your F is going to produce S amount of Al3 plus and 3S amount of OH minus. Okay, so let's count the things you need to set up before you actually solve the problem. Okay, so once you actually got to this point, okay, that's actually one more thing you can write, right? Because you know this constant is 1 times 10 to the negative 33. Okay. So once you write these equations, okay, then you start actually put in the information of your soluble salt. Okay, so here your soluble salt is Al NO33, right? And then you have 0.01 M. Okay, so every time you see these compounds, you don't really care about its whole formula. You only care about the common items you are going to use. Okay, so here, everybody can see that the common ion will be Al3 plus, right? So this is going to be a soluble salt because it doesn't give you the KSP, right? So it means that it's going to be soluble 100%. And then all you care is actually you want to know what will be the Al3 plus that we produce from this specific salt. Okay, since you have 0.01 M of this kind of salt, and then this salt is going to produce 1 Al3 plus. Therefore, you should know that once you store the things inside your solution, it's going to produce 0.01 M, right? And this thing will actually mixed with your solubility coming from your AlOH3. Okay, therefore inside your solution right now, this is actually what you have. Okay, and then if you know that if you're fine with this, then you can actually write your KSP is going to equals to S plus 0.01 times 3S raised to a third power. Okay, and here is actually where I'm going to use the small x approximation. Okay, for the insoluble salt, all this S will be so small. Okay, therefore, your S plus 0.01 can be approximate as 0.01. Okay, so this is actually a small x approximation. Therefore, you can rewrite the first term as 0.01. Second term still stay the same, right? And this whole thing is going to equals to your KSP constant, 1 times 10 to the negative 33. Therefore, 27 S cubed is going to equals to 1 times 10 to the negative 33 divided by 0.01. So your S cubed is going to equals to therefore your S will equals to the cubic root of this whole thing. And you're going to get a number of 1.6 times 10 to the negative 11. Okay. So this is actually how you solve the problem like this using the small x approximation. Okay, so let's recap the last flow. Okay, first one, you need to know what is actually your insoluble salt. Okay, once you identify that, All other species will be the soluble salt that's going to provide the common ions when you write out your chemical equation. Okay? And then you should actually definitely know from the chemical formula how you write out these things and that. Right? You have to pay close attention to your stoichiometry of the ionic species. Okay? And then you put in the common ion concentration. Okay, after you have that, then you dump into your KSP equation. Then use small x approximation. Okay, then solve your solubility. Okay, there will be the proper logic flow to solve a question like this. All right, and you're going to use this logic over and over again in chapter 15. All right, any question for this? So this is actually the most complex. So S, how do I write this, right? Why do I actually apply small s approximation here? Okay. So I say S plus 0.01 is going to equals to 0.01, right? So how do I say, why do I say that? And can I really say that? Okay. So once you do all this calculation, you can see that what's the solubility? What's the order of your solubility? 10 to the negative 11. Okay, 10 to the negative 11, okay? Compared to the 0.01, which is 10 to the negative 2, right? It is 9 order of magnitude difference. Okay, so do you care the small s in the concentration of your Al plus, Al3 plus? You don't really care. Okay, that's why you can write these things. Does that make sense to you? Okay, so in the insoluble salt, the solubility will always be very, very small. Okay, so small x approximation is always valid. Okay, and talking about that is when you do this KSP calculation using your calculator, okay, make sure you put your calculator in the scientific notation. Otherwise, all the number you got will be 0. Everybody know what I'm talking about? Okay, so make sure you put your calculator in the scientific notation mode. Okay, otherwise, you're going to lose your point because you don't know how to use your calculator. Okay? All right, so that's all for the chapter 15. Then we can actually get back to the reviews. Okay, so we'll start from the chapter 13. Go through a few simple conceptual questions, then we start to do some calculation. Okay, and try to follow as much as you can. Okay, if you cannot follow in the in-person lecture, go back and rewatch it. Okay. First question, given the following value of pKa and pKb, select the strongest acid from the list below. Okay, so then give you a bunch of chemicals, a bunch of pKa and pKb. Okay. So how do we actually solve this problem? The idea is actually very simple. Right? So Ka is actually expressed the level of dissociation produced your proton. Okay, to making the acid. The larger the Ka, the stronger the acid. The larger the Kb, stronger base. Okay, everybody understands that concept, right? But here, do you actually get Ka? You don't get Ka, right? What's the things that you get? pKa, right? And that's actually the things you need to know the definition of P, right? Because pKa is negative log of Ka, right? And then because of that negative sign, okay, then you end up with, you actually pick the smaller pKa. Okay, so let me make it clean so you can memorize it. This two is actually equivalent. Okay, so large Ka equivalent to the smaller pKa. Okay, it's just a mathematical operation that it becomes small. Okay, so therefore you have to pick a substance with a smaller pKa. That will be a stronger acid. Okay. Any question for this? I guess not, right? So from this concept, then just look at the number that you have. There are a few substances with pKa, right? So let's start from here. Okay, among the three, which one is actually the strongest acid? HNO2, right? Because it gives you the smallest pKa, right? It's 3 point something, right? 3.37. Okay. But let's do two more substances that we don't know the pKa, right? We only see the pKb, right? So how do you do the pKa of those substances? pK plus pKb equals to 14 too. Okay, so you can actually calculate what the pKa is. All right, but let's actually another way to see these things. If you look at those substances, what are they? It's amine, right? Amine is a base, so it cannot be a stronger acid, right? They're actually both with base. Okay, so from there you should be able to choose the answer that since this one has the smallest pKa, therefore it will be your answer. Okay. Any question for this? Okay, let's do another test. Ka for the base. At first, it's their base, so they can be an acid. Yeah, you can also calculate the pKa of the base using 14 minus your pKb. And then you will see that the number is always bigger than the number for the HNO2. Okay. So we have two base here, right? Which one is stronger? Which one is stronger? Base. And there's three, right? So remember, it's the same concept. Larger Ka, stronger acid. Smaller pKa, stronger acid. Acid and base, they are all that kind of in contrast to each other, right? Every time you switch the same concept to your base, you change your Ka to Kb and acid to base, then everything will be still better. Okay, therefore you pick up substance with smaller pKb. Okay, they will give you a stronger base, right? And use this one as an example, you can see that H3 have a smaller pKb, therefore it will be a stronger base. All right? I hope everybody need to remember this concept, very important. Okay. I guess I will write this so that it's easier for you to see when you actually watch the video. All right? Okay. Question number 2. What is OH minus concentration that has a pH of 12.5? Okay. So this question is interesting because it asks you the OH minus, but it gives you a pH value, right? So I will always suggest if you want to calculate the photon concentration, you use pH. If you want to calculate the OH minus concentration, you use pOH. Okay, let's actually go habit now. Okay. Since here you want to actually calculate the OH minus concentration, right? So you want to actually starting from the pOH. Okay, but here it tells you your pH equals to 12.5. Therefore, the pOH is going to equal to 14 minus 12.5, which equals to 1.5. Right? Then you know the pOH was defined as negative log of OH minus concentration. Okay, so the way you remove log is what? You times 10 to the power of lab, right? So your OH minus concentration will simply equals to 10 to the negative 1.5 power, which give you a value of 3.16 times 10 to the negative 2. Okay? So you should definitely actually know the definition of pH, pOH, pKa, pKb by now. Okay, you should also know that pH plus pOH equal to 14. Okay? Okay, next questions. Okay, one of the things that you'll definitely be tested is actually to write out the conjugated partner, okay, of the things. Okay? So if you read these questions, you want to give the conjugated base of HSO4, right? So the question is you want to know the conjugated base. Okay, and then the things you have is HSO4 minus. Okay. So to find out the conjugated base, the way you do is actually you subtract 1H plus from the molecule that's given. Right? To obtain the conjugated acid, what is actually you add H plus to the given substance, right? So this here is actually asking for the conjugated base, right? Therefore, you know you need to actually minus a proton, right? So if you minus H plus, then you end up with SO4. You minus one positive charge. You start from negative 1, right? Right now you end up with negative 2. Okay, so this is the conjugated base of HSO4 minus. Okay. And today, I want to know the conjugated acid of HSO4 minus. Then the things you do will be you plus H plus, right? Then you end up with H2, SO4. Okay, you start from negative 1 charge, but because this positive charge, they cancel each other, therefore you end up with a neutral species. Okay, so make sure you know how to write the conjugated partners of the given substance. Okay, you definitely have one of these type of questions in your midterm. Okay. Question number 4. calculate the pH of 0.5 m ammonia solution. Okay. Your Q apparently is actually calculate the pH. But every time you see this question, right, I tell you, you must determine what kind of solution that you have. Right? What kind? With base, right? So, you know you want to calculate the pH of weak base. Okay, right now I'm going to always use A minus to represent my weak base. All right? So, you know the question that you want to calculate pH of a weak base. Okay? Data. Concentration of the weak base. I don't really care what it is, but I know it's actually weak base, right? Concentration of my weak base is what? 0.5 m. Kb is 1.8 times 10 to the negative 5. Right? Those are your data. And then now we know, since it's actually a weak base, right? You calculate your OH minus concentration from your weak base concentration times your Kb, then take the square root of that. Then you're going to have 0.5 times 1.8 times 10 to the negative 5. Therefore, you know your OH minus concentration is going to equals to 0.003. Therefore, your pH, so POH, is equal to negative log OH minus concentration 0.003. That's equal to a value of 2.52. Therefore, you know your pH is going to equal to 14 minus your POH, 2.52. That gives you a value of 11.48. And that will be the answer. Okay. So again, when you can read the questions, make sure you know what kind of solution that you have. Will make this calculation very straightforward. Okay. So if you have all these concepts, solving a problem like this only take you maybe a minute, right? But if you doesn't have this concept, it will take you actually very, very long, but you don't have that much time. Okay. So make sure you can do this. Okay, so that's actually how you do your question number 4. Okay. And then the next question, I want to go to this one. Okay, so very similar questions. Okay, it says calculate the pH of 0.5 m solution of sodium acetate. The Ka of acetic acid is 1.8 times 10 to the 5. Okay. You know you want to calculate the pH of a solution. A solution. Then this is how everybody gets stuck, right? Everybody finds the question I just went through, right? It's exactly the same question still. Just a little bit twisted, right? And then right now everybody got stuck. Okay, so now tell me what kind of solution do we have? With base, how do you know? Yes, so I tell you guys, okay, just even if you don't know what it is, right? Look at the Ka or Kb first, right? In this question, both provided. Ka is provided, right? Yeah, Ka is provided. Okay, and then if you look at the substance that have the Ka, is CH3COOH, right? CH3COOH apparently is actually weak acid. Okay, then you look at your question again. Do you have CH3COOH? You don't. What you have is actually NaCH3COO, right? They are different substances, but they were put in together in one single question. There's a good reason for it, because they will be the conjugated partner of the substance that have the Ka or Kb value, right? Since right now you know the substance has Ka was provided, right? So the things that I'm going to ask you will be its conjugated base, right? Therefore, again, you come back to the same question. Okay, you're going to calculate pH of a weak base solution. Okay, like we said in the previous question, will be exactly the things you're going to use to solve this problem. Okay, the only thing that will be different is what? In the previous question, you can do Kb directly. Okay, here you will have to calculate your Kb to solve your pH. Okay, everybody understand and totally follow what I just said? Okay, I want to actually make these things crystal clear to you so that you can actually know what kind of solution that you have. Let's go back to this question again. Okay, now read this question again. It says calculate the pH of 0.5 m solution of ammonia. Okay, and then it gives you NH3. Okay, so ammonia is NH3 itself. Okay, and the Kb that's given is for ammonia 2, right? So these two are consistent. Therefore, you know the things you have inside the portion is a weak base. Okay, in contrast, the question we just went through is asking you about this, but it gives you that. These two are different species, but was put together inside a single question. Okay, therefore you know if it gives you Ka, that means this one is a base, right? Therefore you can quickly identify. Here we calculate a pH of a weak base solution. All right? Then once you have that, then you can actually come to here. What's the A minus concentration? 0.5 m. Right? And then you want to know the Kb. But here you realize that you don't have Kb. Therefore, you can actually back calculate your Kb using Kw over your Ka, which is 10 to the negative 14 divided by 1.8 times 10 to the negative 5. Which is going to give you a value of 2.38 times 10 to the negative 9. Okay? Then you can calculate your OH minus concentration equals to square root of A minus times your Kb equals to a square root of 0.5 times 2.38 times 10 to the negative 9. Therefore, you can calculate your OH minus sorry, wrong number. 5.56 times 10 to the negative 10. Okay, so then your OH minus concentration will equals to 1.67 times 10 to the negative 5. Therefore, your pOH, which is equal to negative log of your OH minus concentration, 1.67 times 10 to the negative 5, will give you a value of 4.78. Therefore, the pH is going to equal to 14 minus your pOH, 4.78. You end up with your pH equals to 9.22. Okay. I hope by now you see these things more clearly. Okay. Everybody's fine now? We good? One more time. Okay, read the question properly. Okay. Apparently, again, we're going to calculate the pH of a certain solutions, right? There are two species showing up. Okay, what kind of solution do we have? Everybody can see we have weak acid? Okay. Yes, we do have a weak acid, right? Because the species that was given the KD is CH3NH2, right? Which is actually different from the species that the question is asking for the pH, right? So in this actually, whatever species this is, it must be the conjugated acid, right? Therefore, you know you have a weak acid, which I always use HA to represent it now. Okay. Then data. Okay. What's your weak acid concentration? 0.422 N. I want to know the Ka, but I don't have it. Therefore, Kw divided by your Kb. 4.2 times 10 to the negative 4. They will give you a value of 2.38 times 10 to the negative 9. Okay? Once you have your photon concentration, you also have weak acid concentration, once you have your Ka, photon concentration equals square root of HA times your Ka equals to square root of 0.422 times 2.38 times 10 to the negative 9. Therefore, your photon concentration is going to equals to 3.17 times 10 to the negative 6. Therefore, your pH is going to equal to negative log of your photon concentration, 3.17 times 10 to the negative 6. You're going to get a pH value of 5.50. And that will be your answer. Okay. So I want to make sure that everyone follow this very simple tips. Okay, so really know what kind of solution that you have will greatly speed up your calculation. Okay, so that you're going to have more time for other more challenging questions when you do your midterm. Okay. Okay, so once we're done with these simple calculations, then we can actually go to something a little bit more complicated. Okay, it says a certain temperature, the percent dissociation of this specific acid. And then in this specific concentration is 10%. XU the Ka. Okay. So the question is actually asking you to calculate the Ka of a weak acid. Okay. And then the key information here or keyword here is something called the percent dissociation. Okay, so you should know the definition of that. The percent dissociation. So what it means is the proton concentration over the weak acid concentration times 100%. Okay, so that's actually the definition of percent dissociation. Okay, for the weak acid. Okay. So once we have this idea, then you can write out other things, right? You know your weak acid concentration is what? 1.63. Okay, and then your percent dissociation is 10%. Okay. And then you want to calculate the Ka, right? So how to handle this? Because we know how to calculate the proton concentration of a weak acid. Everybody can see that, right? Proton concentration is square root of weak acid concentration times the Ka, right? Can you put this, substitute this guy with that guy? That's what you're going to do. Okay? Therefore, you want to actually rewrite this percent dissociation equation a little bit differently. You're going to write this. Okay? So that's what you're going to write. Okay. And then this thing's equal to 10%, right? Meaning it's 0.1, right? Okay. Do you have your weak acid concentration? You do, right? 1.63. You have this, you have that. In this equation, the only unknown is what? Your Ka. Right? So all you need to do is actually plugging all the numbers. Therefore, you have square root of 1.63 times your Ka divided by 1.63 is going to equal to 0.1. Then you can solve your Ka. It's going to equal to a value of 1.63 times 10 to the negative 2. And that's it. Okay. So this is how the extension of the things that you already know. Right? All you need to do is actually know the definition of your percent dissociation. Okay, any questions for this? Okay, so I have one thing to ask you guys. So this is the percent dissociation of a weak acid, right? If today I change this one to a weak base, okay, what's going to change? Yes, your H plus become OH minus. Your weak acid become weak base. Okay, structure-wise, they are exactly the same. It will be the OH minus concentration over the weak base concentration. But again, you can calculate your OH minus concentration using square root of weak base concentration times the Kb. Yes. Okay. So this is actually a complex extension, or you can call it actually a transformer of the weak acid concentration calculation. Okay. Okay, so those are the simple questions. Now we go to something that's actually more interesting. Okay. So now look at this. Okay, read this question carefully. Okay, so it says calculate pH of a solution by mixing 50 ml of this and then 25 ml of lead. Okay, and it tells you the Kb of NH3 is this. What's the things you want to solve? You want to solve the pH of certain things, right? What kind of solution do you have? Copper, very good. Because right now you can see your NH3 and then the NH4 here, right? So very important. Once you know you have a buffer, there's actually only one equation to go to. Okay, I hope you see the power of knowing what solution that you have. Okay. Then we can write out our data, right? So one is actually you have, this is your weak base, right? So A minus. Concentration, 0.1 m, 50 milliliters. Your weak acid is 0.1 m, 25 milliliters. Okay. And then you have your Kb, 1.8 times 10 to the negative 5. So that's all the data that you have, right? But since you already know you are going to use the HH equation, you will need your Ka, which is 10 to the negative 14 divided by your Kb. That's going to give you a value of 5.56 times 10 to the negative 10. Okay? So once you have all this information, the next thing is actually, you want to calculate pH equals pKa minus the log. You go weak acid over conjugate base concentration, right? Okay, so the first step is simple. Negative log of your 5.56 times 10 to the negative 10. Okay, we'll come to a second term. What's your weak acid concentration after you mix it? What's the concentration you should actually put in there? 0.45? To you? Okay. Imagine right now you're actually sitting alone inside class and you encounter this question. Okay, what do I put in? 0.5. If you put in 0.5, I feel sorry for you. Okay, so every time when we look at this type of questions, right? Remember here, even I say this next HA, next log HA over A minus, right? Okay. I would suggest you think about it as actually more. Okay? Because eventually these two, your HA and A minus, they're going to put into the same container, right? That means your HA and A minus, their volume will always be the same, right? So the ratio between the two is actually a ratio between their moles. Okay? So they'll actually make your life a lot easier because if you look at this, you have 0.1 in 50 mil, meaning you have 5 millimole, right? 0.1 times 50. That give you 5 millimole. This one will be 0.1 times 25. Right? Then you actually see how many moles that you have inside the solution at the very end. Okay? And then you can just plug the moles into this equation because the volume is actually the same. So the ratio between your concentration becomes the ratio of the moles. Okay. So HA you have 2.5. A minus you have 5. Okay. That means the ratio between the two will be 1/2. Okay. And then once you do that, you can get your pH. This one equals to, okay, the first one is 9.26. The second term with the negative sign will give you plus 0.3. Therefore, your pH is equal to 9.6. Okay. So, yes. It doesn't really matter. Okay, because it's ratio, right? As long as it's actually consistent throughout, you are fine. Okay. Yeah. Any other questions? Okay, so let me remind you again, every time we use the HH equation, right? Even though I always say the concentration of acid over base, right? I would suggest to use mole to avoid all the confusion. Okay, because the volume of these two species will be the same since they're actually in the same containers. Okay, so the concentration ratio will be equivalent to your molar ratio. Okay, and then since it's actually molar ratio, as long as they are consistent, if you both use moles, then use mole for both. If you want to use millimole, use millimole for both. As long as they're actually consistent, they will cancel out. Okay, so that's actually how you handle a question like that. Okay, so then we can look at these questions. Calculate pH when 0.68 grams of one species to a volume with certain concentration of the other species. Okay. It's very similar question. Okay, we just do the practice one more time. We want to know the pH of a solution. A solution. Okay, so every time we read the questions, right, try to highlight the things that you have. And then really pay attention to what What are they? Conjugated acid and base. Therefore, you have a buffer. I'm always amazed how difficult it is to actually recognize the solution as a buffer. Okay, it's exactly the same questions. Okay, so if you look at this too, if you look at those two species, can you recognize they actually conjugated acid and base? Right? So, can you actually take one more step from this? Become C6H5 COO minus. And then you look at this and that. Can you tell they are actually conjugated acid and base? Okay? So practice this a lot at home. Okay, you said for 1 week to practice this, so you're fine. Okay? I don't hope that when you sit inside the class alone, only with your calculator and your sketch papers, and read, okay, I have C6H5COONA, C6H5COOH, and I cannot say it's a buffer. I don't want it to happen to you. Okay, so do practice. It's actually very similar to the question that we just went through previously. Very, very similar. Okay? All right, yes, so they are going to have a buffer. So how do you calculate the pH of the buffer? You use the HH equations, right? Then you go to your data. This one apparently is actually your A minus. Then you have 0.68 gram. Its formula weight is equal to 144.1. Your weak acid is 0.5 N, 18 grams, right? And then you have the Ka equals to 6.5 times 10 to the negative 5. Okay. Then you know you can calculate your pH equals to your pKa minus log your weak acid over A minus. Okay. First term, you already have Ka, right? So it's negative log 6.5 times 10 to the negative 5 minus log. So here I say use what? Use mole, right? So to calculate mole, you can use this 0.5 times 18. That's going to give you 9 millimole. Okay. To calculate the mole of your A minus, it will be the mass divided by formula weight. Okay, so this will give you 4.72 times 10 to the negative 3 moles, which equals to 4.72 millimole. Okay, make sure the unit is consistent. Okay. So once you have this, then you know your acid is 9, your base is 4.72. Then you're going to have 4.19 minus 0.28. Therefore, your pH is equals to, oh my God, what's going on? Okay, so your pH is going to equals to 3.91. All right. So do you see the same pattern is repeating now? Yeah. So make sure you know 100%. You must know. If you don't do well for your method, you must know if you have a proper solution. Okay. Any questions for this? If I can only go through 2 more questions. Okay. Okay, so calculate pH of a solution by adding 20 ml of 0.1 NaCl to 80 ml of buffer that is comprised of 0.25 N amine and 0.25 N NH4Cl. The Kb of the amine is certain number. Okay. What kind of solution do you have? How do you know? Because it's buffer, right? Yeah, so besides buffer, this one is actually different from the previous questions. Okay, what's the differences? You add in what? A strong acid. Okay, I add in a strong acid, right? So you have 3 species here, right? And then I want you to know that the buffer is 0.25 N, amine 0.25 N, weak acid, right? And then you add in another part, which is actually your strong acid. Okay? So the idea is what? Strong acid will kill all the bases. Okay, regardless whether it's strong or weak, until it got fully consumed. Right? So that's actually the main idea here. Okay. At this moment, just look at the number, it's hard to say who is actually more abundant. Okay. Therefore, you don't know what solution that you have, right? Because if you have more strong acid, okay, then the weak base, then all the weak base will be consumed, right? Then inside your solution only has strong acid and weak acid. And all you can care is actually strong acid concentration that remains, right? The other situation is actually all the strong acids consumed. Okay, then so if you have weak base remain, then it's still a buffer. Okay, so you have to figure out what is actually the situation that you have. Okay, so we'll actually leave this one for now, and we'll come back this one later. Okay, we need to do some analysis. Okay, then let's look at our data. Okay, since this thing is going to be adding a strong acid, right? Therefore, you know the species that's going to interact with your strong acid will be your weak base, right? So weak base is going to interact with your strong acid. That's going to produce the weak acid, right? So that is actually the thing that I have here. Okay. Then you actually start to compute the mole of every single species. Okay. For your weak base, you have 0.25 M, right? And the volume is 80 milliliters. Okay. Therefore, you have 0.25 times 80. You have many millimoles, right? So this is actually 20 millimole. Okay. And then you know the conjugated acid is the same concentration. That means this guy is also going to have 20 millimole, right? Because you also need to use 0.25 times your 80. So they're going to have the same amount to start with, right? Then you start to actually looking how much strong acid I add in. I add in 0.1 N, have 20 milliliters, right? Therefore, I know I have 2 millimole, right? So, who is actually a limiting reagent in this case? Strong acid, right? So your strong acid will be fully consumed. Therefore, you know You will minus 2 plus 2. At the end, yes, you don't have any strong acid, but you have 80 millimole of the base, 22 millimole of your weak acid. Okay? So up to this point, then we can know that's the final situation I'm going to have, right? Then you can ask yourself, what kind of solution do I have? What kind? A buffer solution, right? Because right now, again, you come back to a situation, you only have the conjugated acid-base pair solution. Okay? Therefore, you know, you can come back to your Q here. You actually have a buffer solution. Therefore, pH equals to pKa minus log weak acid 22 base 18, right? Do you have Ka? You don't. Okay, you actually have Kb, right? So you need to actually calculate your Ka by doing this. 10 to the negative 14 divided by the Kb, 1.8 times 10 to the negative 5. Then minus log 22 over 18. And then when you do this calculation, you can get your pH is going to be equals to 9.17. Okay. So any question for this one? So this is actually one more layer of complexity compared to a simple buffer calculation, right? So I want everybody to see the things that have happening so far. Okay. So we start to talk to you about this simple definition, right? What's Ka, what's Kg, what's pKa, what's pKe. Then what's pH, what's pOH, what's conjugated oxygen, right? Then we start to calculate the constant pH of weak acid with base, right? And then we calculate the pH of buffer. Now pH of a buffer solution with strong acid adding. Okay, so I hope you see these things is getting more and more complicated. Okay, but if you can see the patterns, it's actually all very simple. Okay. Okay, so let's look at this. Determine the volume in milliliters of 0.781 mKOH that's needed to reach half equivalence point in the titration of something else. Okay. What's that pure here? Yes, equivalence point and titration. Right. So this actually tells you that we actually head into chapter 14 now. Okay. Okay, so the Q is want to us to calculate the half equivalence point, right? And then you want to actually analyze these things a little bit. You have your KOH and then HClO. Okay? KOH is a strong base, right? So in this case, you will be your isomer. Okay. Of course, you first need to know that HClO is actually a weak acid because weak acid cannot put up the titan. Therefore, you know your KOH that you're attacking here. Okay. So hydrogen is your KOH. And then you have concentration 0.781 N. Analyte is HClO, a weak acid. You have 0.494 N. Volume is 49.8. Okay. So every time when you see these titration questions, okay, you can always first calculate your equivalence point. Okay, and the way you calculate your equivalence point is actually very simple. Concentration of your titrant times your VEP is going to equal to concentration of your inner line times the volume of your inner line. And then here, titrant concentration is 0.781. VEP is actually the things you want to calculate first. Concentration of your inner line is 0.494. Volume is 49.8. Therefore, you know your VEP is going to equal to 31.45. Okay, so you can know you need to add in 31.45 ml of your titrant into your solution so that the mole of your titrant will equal to mole of your analyte, right? But here it doesn't really ask you for VEP. It actually asks you for the half of the VEP, right? Half equivalence point. Therefore, the answer will be this divided by 2. That's going to give you a value of 15.7 milliliters. So this will be the answer. Right. So we actually went through very similar, not always like exactly the same amount, very similar questions in the in-person lecture. Okay, and then the things that we say over there is that once you know your half equivalence point, okay, at this point, what's going to happen in flood? We know here you analyze actual weak acid. The titrate with a strong base. Therefore, you're going to produce H2O plus A minus. Okay? So, because it is at half equivalence point, okay, so the mole of your HA will be twice than the mole of your strong base. Everybody follow this? At half equivalence point, the mole of your titrate, which in this case your OH minus, is half of the mole of your analyte. Okay? So what this means is that all your titrant will be consumed and you're going to produce its conjugated base, right? So at the end, you're going to have the same amount of weak acid as conjugated base. That means at this specific point, what kind of solution do you have? A buffer. Okay? So if I ask you to calculate the pH of this solution at this specific point, at the half equivalence point, do you know? The pH can be computed using the HH equation, right? What's the mole of your acid? It's N/2, right? The mole of your conjugated base. That means actually this will give you a value of 1. That means the second term will become 0, right? This means pH is equal to. Okay, so this is actually a very specific case. Okay, at half equivalence point. Okay, if they ask you to calculate pH, the answer will be just your pKa. All right. So I think that's it for today. We're going to finish the remaining on Thursday.